Colloids, sometimes called colloidal dispersions, are mixtures that are between a clearly heterogeneous mixture and a solution. The particles are small enough that we cannot see them with the naked eye, and probably not with a microscope, but they are not broken apart into molecules or ions that are independent of each other. There are many different types of colloids based on the state of the dispersant or solvent-like substance and the state of the dispersed or solute-like substance. The ones most commonly discussed are dispersed in a liquid, where a gas dispersed in a liquid is a foam, a liquid dispersed in a liquid is an emulsion, and a solid dispersed in a liquid is a sol. When we have a solid dispersant, a gas dispersed in a solid is a solid foam. A liquid dispersed in a solid is a solid emulsion, and a solid dispersed in a solid is a solid sol. Things dispersed in a gas, the most commonly encountered colloid, are called aerosols, with a liquid dispersed in a gas called a fog and a solid dispersed in a gas called a smoke. Note that any gas dispersed in another gas is a solution. The term used for one type of air pollution is smog, which is a mixture of smoke and fog, implying that there are both liquid and solid particles dispersed in the air. We can identify the presence of a colloid by the presence of the Tyndall effect. A strong beam of light is shined through a mixture. If the beam is scattered, as it is in the glass on the left, then the particles are large enough to be a colloid. In a true solution, the glass on the right, the particles are too small to scatter light in this way. We see the Tyndall effect in nature all the time. The redness of the sunset and sunrise is due in part to the scattering of light by the particles in the air. We can often see sunlight being scattered off particles in the air when beams of light shine into a darker area. In biological systems, it is a common situation for large molecules that are basically nonpolar to have portions that are polar or even charged. The polar end is attracted to water, the nonpolar end to other nonpolar things. One example of this is soap, either the salt of a long-chain fatty acid or an artificially made detergent. In this example, the sodium salt of stearic acid, sodium stearate. One end is charged and dissolves in water. The other end dissolves in the nonpolar oils and dirt. These molecules aid in the emulsification of fats and other nonpolar stuff by creating a layer of molecules on the surface of the fat whose nonpolar ends are dissolved in the fat and whose polar ends can dissolve in the water, thus pulling the clump into solution, really into an emulsion, so that it can be rinsed away.